name is Felix, and behind the camera today is Alex the Shields. And today we're going to be discussing Ohm's law in DC circuits, which was theorized by the German physicist Sir George Ohm. The equation for Ohm's law is the voltage equals the current times the resistance. As you can see, it is a fairly simple equation. Ohm's law's equation, you can see that the voltage is directly proportionate to the current times the resistance. And if you want to find the current or the resistance, it can be pretty easily found by using this triangle right here. For example, for voltage, you just cover the V, and you see it's I times R. If you want to find the current, you cover the I, and you'll get V over R. And likewise, you could, if you want to find the resistance, you cover the R, and you'll see that R can equal V over I. And now for the next part, we're going to show how Ohm's law can be used in DC circuits. Now we'll be discussing DC circuits. In a series circuit, the current will stay constant across the entire circuit, and the voltage will drop across each resistor. And as well, the total voltage across each resistor will equal the total voltage in the entire circuit. Well, this one. Now when we look at parallel, it acts a little different. In parallel, the voltage will stay constant in each branch of the circuit. But however, the current will vary in each branch, and the current will want to travel where there is least resistance. But after they reach the junction here, the total current of these two will equal the same current that went in on the other side. That's how we can use Ohm's law to solve DC circuits. Now, in series circuits, as we talked about earlier, the total current across each resistor will be the same. However, the voltage across each resistor will not be the same. There'll actually be a voltage drop. Now, when solving for these kind of circuits, you want to find the equivalent resistance or the total resistance of the circuit. So you can first look at right here that the total EMF will be equal to the amount of voltage drops that are across these resistors. Those total voltage drops will equal the EMF. Now you can replace each voltage with their respective resistance times the total current, as you can see when you cover the triangle again, equals current times resistance. Now, like we said before in a series circuit, the total current will equal the same in each resistor, so that means that you can cancel out the currents, and your equivalent resistance will equal the total of the two resistors. Now, when we talk about parallel, as we mentioned before, the voltage across each branch will be the same. However, the current will not. It will vary depending on the resistance in each branch. Now, same thing, we're going to want to look for the total resistance or the equivalent resistance to solve this kind of circuit as well. Now, you can replace your equation here with the voltage over the resistance. We'll go back to the triangle. Voltage over resistance. And our equation will look like this. Now, as we said before, the voltage will be the same in each branch. So that means that we can cancel our EMFs, and you'll be left with the inverse of the equivalent resistance. Or you can write it out like this: the inverse of the total inverses of the resistance. Now my partner Alex will demonstrate an example problem using what we have learned today.
Alright, so today we're going to be looking at this circuit, and we're going to be using Ohm's law to determine these three things, the total current going through the charge, the current in each resistor, and of course that'll require us to get the equivalent resistance. So we're going to start with these two circuits, and we notice that they're in parallel, or two resistors, I mean, they're in parallel. So what we're going to do is, when they're in parallel, you add them up inversely, and that will get you your second current with the two values. So that's going to be 1 over 100 plus 1 over 250 equal 100. Let's call this one R1, and then we'll call the other one R2. Oh, then we have R1, R2, RA, RB. Plus 1 over 200 and we plug that into the calculator. And we get this to equal 71.42. And this one to equal 127.27. Okay, and so those are two values for these resistors now. 71.42 and 127.27. Okay, so we notice that these two resistors, they are in series, so we're going to add them because we add resistors in series. And so we got 127.27 plus 71.42. That's going to give us an equivalent resistance of 198.7. And put that in the box because that is important. And what we're going to do with that, we're going to plug it into Ohm's law, V equals I R, to find the current running across that resistor, and then we could use different properties of resistors just to find the current running through each of them. So we know the voltage is going to be 24. We know that the resistance is going to be 198.7, and we're trying to find out what I is, and so we're going to divide 24 by 198.7. That's going to give us a current of 0.1207 amps. Okay, so we have our final current, and it is 0.1207 amps, and we know that when the resistors are in series, that it will be the same in both of them. So we know that the current for both of these is going to be 0.1207 and 0.1207. And we could plug that back into Ohm's law, plug back into the equation to find the voltage across both of these. So we're going to have voltage equals, we know that our current is 0.1207, and we know that our resistance for this bottom one is going to be 127.27. And we can plug that into our calculator to find out what it equals. We know that the voltage running across the bottom one is going to be 15.37, so we'll call that voltage 1. And then solve for the second one. Which we're going to have a resistance of 71.42. Plug that into a calculator. And you're going to get a voltage that's running across that one of 8.62. And we know that voltage will be the same when they go back to parallel. So the voltage running across R1 and R2 will be the same. And the voltage going across R3 and R4 will be the same. So since this one had the resistance of 127, we know that R3 and R4 will be 15.37 volts and 15.37 volts. And we know that the other one will be 8.62, and this will be 8.62. We're at 9 units. This would be amps. Okay, and so now we have the voltage running across each one of the resistors, and now we're going to find the total current across each one of them. Now we're going to find the current in each resistor using Ohm's law, and we're going to do a little algebra with this guy because we're looking for the current. We're going to have current equals voltage over the resistance, and we have all of our different voltages and we have all of our different resistances, and so we're going to just plug and chug. So we have I1, we'll use the 100 first, equals 8.62 volts divided by 100 ohms. And that's going to get us 0.086 amps. And for the second one, it's going to be I2. It's going to equal 8.62 volts divided by 250 amps. So it's going to be 3 plus 2 divided by 250 ohms rather. And that's going to get us 0.0345 amps. We're going to solve for I3, which is going to equal 15.37 volts divided by 350 ohms. That'll get us 0.0439 amps. And lastly, we're going to solve for I4, which is going to be 15.37 volts divided by 200 ohms. Which is going to give us 0.0769 amps. And that's Ohm's law.
Looking at our results, we can back check our answer with what we know about Ohm's law in DC circuits. Our calculated current will be the same across the entire circuit until it crosses the 4 resistors in parallel. If we redraw the circuit as 2 resistors in series, as seen on the right, the same amount of current will flow in each resistor combinations. Once we form our original circuit, the current will want to travel the path that has the least resistance. As you can see, resistors R1 and R4 have the lowest resistance in their respective branch and the highest current. The total current in each branch should equal the total current that was calculated, and the sum of the voltage drop in each branch should add up to the value of the original EMF source.